Today, we're diving into a really cool mystery from the world of particle physics. We're going to look at a strange, lopsided pattern that actually gives us an incredible peek into the very heart of matter.
I mean, that's a great question, isn't it? It feels like it breaks a fundamental rule of symmetry. But get this. This isn't some brain teaser. It's a real-world observation, coming from the most powerful machines humans have ever built. And hidden inside this lopsided pattern is a huge clue about how our universe is put together. So, you ready? Let's crack this case.
All right, so our story starts at places like CERN, which is home to the Large Hadron Collider. This is where scientists take protons, the building blocks of atomic nuclei, and whip them up to nearly the speed of light. Then they smash them together, creating this spectacular fireworks show of new exotic particles. Now, while watching these collisions, they started noticing something odd. They saw a particle called the W boson being created, but it wasn't an even split. They were consistently making more of the positively charged version, the W+, than its negatively charged twin, the W-. And that right there is the big mystery. We're slamming identical particles into each other. So why the preference for one over the other? It's kind of like flipping the exact same coin a million times and getting way, way more heads than tails. Something's up. And the answer, as it turns out, isn't in the collision itself, but deep inside the protons we started with. So to figure out why the results are so lopsided, we've got to get to know our main suspect, the proton. And the very first thing to know is that a proton is not at all what you might think it is. See, it's not some solid little sphere. It's actually a chaotic, bustling, super energetic bundle of even smaller, more fundamental particles. And these particles are called quarks. So think of it less like a tiny marble and more like a tiny, buzzing beehive. Okay, so inside this proton, it's not just one thing. You've got two main players. First, you have what are called valence quarks. Think of these as the proton's permanent DNA, its core recipe. And that recipe is always, always 2 up quarks and 1 down quark. Then you've got this wild, chaotic thing called C quarks. This is like a constant fizz of energy, where pairs of quarks and their antimatter opposites just pop into and out of existence, super fleeting. But the really important part, the thing you have to remember for this whole mystery, is that core recipe. 2 high energy ups for every 1 high energy down. That imbalance is everything.
So now we know what a proton's really made of. Let's see how that internal structure totally dictates what happens in the heat of the moment, what it actually takes to forge one of these W bosons in a collision. In the utter chaos of 2 protons smashing together, it's really their little internal quarks that are doing all the work. To create a positive W+ boson, something very specific has to happen. An up quark from one proton has to smack into an anti-down quark. That's the antimatter version of a down quark from the other proton's C. They annihilate each other, and boom! That flash of energy is the new W+ boson.
And just like that, we've got all the puzzle pieces on the table. We know protons aren't symmetrical on the inside, and we know the recipe for making a W boson. So let's put it all together and solve this thing. So here's the bottom line. The whole mystery just boils down to a game of odds. Inside every single proton that's flying around that collider, there are 2 high-energy up quarks just waiting to make a W+, but there's only 1 high-energy down quark available to make a W-. And voila! This chart shows you exactly what happens. Because you've got twice as many of the key ingredient for a W+, those high-energy up quarks, you're just going to make more of them. It's that simple. It's not some deep, dark magic. It's just a numbers game. The lopsided results we see on the outside are a perfect mirror of the lopsided ingredients on the inside. But wait, there's more. It's not just about the numbers. See, those high-energy valence quarks give the new W boson a really powerful forward kick. And since the W+ is much more likely to be born from one of these energetic guys, which are carrying most of the proton's momentum anyway, it tends to get a bigger shove, sending it flying forward way faster than the W-. This quote really nails it. Now, rapidity is just a fancy physicist term that combines a particle's speed and direction. Basically, it's a super precise way of measuring that forward kick we were just talking about. So what this is really saying is that the pattern of particles we see flying out of the crash is a direct one-to-one map of what was inside the proton in the first place. The lopsided spray is a perfect echo of the proton's lopsided guts. So, case closed. But you might be thinking, okay, that's a neat puzzle, but why is this a big deal? Why does it actually matter to science? It matters a whole lot because this simple lopsided measurement isn't just some scientific curiosity. It's actually one of the most powerful tools we have for getting a good look at the fundamental nature of matter. You see, by meticulously counting how many W plus and W minus bosons pop out, and by measuring exactly how big of a kick each one gets, scientists can build an unbelievably detailed map of the proton's interior. This isn't just about confirming what we think we know. It's about stress testing our entire theory of the universe, the Standard Model, to the absolute limit. It literally turns a giant particle collision into a high-resolution proton scanner. It lets us see the secret lives of quarks. And that kind of leaves us with one final thought, doesn't it? The solution to this huge mystery about the building blocks of you, me, and everything, it wasn't some wild, undiscovered particle. It was found by just carefully looking at a simple, lopsided pattern. It really makes you wonder, what other cosmic secrets are out there hiding in plain sight, just waiting for us to spot the right pattern?